Have you ever wondered why does time only move forward? It's a question that has puzzled philosophers and scientists alike for centuries. Time, as we perceive it, has a peculiar trait. It's unidirectional. We remember the past, but not the future. We can see the effects of time, but we can't rewind or fast forward it. But why is that? Welcome to the fascinating mystery of the universe. This enigma takes us to the concept of the arrow of time, a theory put forth by British astronomer Arthur Eddington in 1927. The arrow of time points from the past to the future in the direction of increasing entropy or disorder. But what does entropy have to do with time? Well, this brings us to the second law of thermodynamics. In simple terms, this law states that the entropy of an isolated system will never decrease. It either increases or remains the same. It's like a cup of hot coffee in a room. Given time, the coffee will lose heat to the room until both are at the same temperature. The coffee doesn't spontaneously get hotter and the room doesn't get colder. This is entropy in action. Now, apply this to the universe. Think of the universe as a closed system. At the moment of the Big Bang, the universe was in a state of low entropy, highly ordered. As time progressed, the universe expanded, stars formed, galaxies clustered, and entropy increased. The state of the universe moved from a highly ordered one to a less ordered one, from low entropy to high entropy, thereby giving a direction to time. So why does time move only in one direction? It's because of the second law of thermodynamics. Time moves in the direction where entropy increases. It's the nature of our universe to evolve from order to disorder, from the past to the future. So, in a nutshell, time moves forward because the universe is in a constant state of increasing entropy. Did you know that the human eye can only see about 0.0035% of the entire spectrum of electromagnetic radiation? Let's unpack this. Imagine a vast cosmic canvas buzzing with an array of frequencies. This is the electromagnetic spectrum, ranging from the very low frequency of radio waves to the high frequency gamma rays. The spectrum is a radiant array of electromagnetic energy. However, our eyes can only detect a tiny sliver of this spectrum. This tiny fraction is what we call visible light, the colors we see every day. Now let's talk about the unseen part of this spectrum. First up, we have ultraviolet light. It's just beyond the violet end of the rainbow we see. It's invisible to us, but not to all creatures. Some birds and insects, for instance, can see ultraviolet light. It's also the part of the spectrum responsible for giving us sunburn. Then we have the other side of the visible spectrum, infrared. This is the heat you feel from a fire or a warm pavement. It's invisible to our eyes, but we can feel it as warmth on our skin. Some animals, like snakes, can see in infrared, allowing them to hunt in the dark. Next, we have X-rays. You may know them from visits to the doctor, but they are also a part of the electromagnetic spectrum. They are used in medicine because they can pass through our body and produce images of our bones. Lastly, we have gamma rays, the most energetic part of the spectrum. These rays originate from the hottest and most energetic objects in the universe, like supernova explosions and regions around black holes. But don't worry, our atmosphere protects us from harmful gamma radiation. So, while we might feel that we see all there is to see, our view of the world is just a small fraction of the whole picture. Our universe is teeming with unseen energy, just beyond our vision. We're blind to it, yet it's integral to the world as we know it. So there is an entire unseen world around us that our eyes cannot perceive. Ever heard of a cat being both alive and dead at the same time? Welcome to the strange world of quantum mechanics. Quantum mechanics, a fundamental theory in physics, is known for its outlandish concepts that defy our everyday understanding of the world. It describes nature at the smallest scales of energy levels of atoms and subatomic particles. Yet its implications reach out to the vast expanses of the universe. To illustrate the bizarre nature of quantum mechanics, let's delve into the famous thought experiment called Schrödinger's cat. Conceived by Austrian physicist Erwin Schrödinger, this experiment poses a scenario where a cat in a sealed box could be both alive and dead at the same time. Sounds absurd, doesn't it? The experiment goes like this. A cat is placed in a sealed box with a radioactive substance which has a 50% chance of decaying within an hour. If the substance decays, it triggers the release of a poison that kills the cat. If it doesn't decay, the cat remains alive. According to classical physics, the cat is either alive or dead based on whether the substance has decayed or not. But here's where quantum mechanics throws a curveball. It suggests that until we open the box and observe the cat, it exists in a superposition of states, which means it's both alive and dead simultaneously. The act of observation collapses this superposition into one of the possible definite states. This principle of superposition is one of the cornerstones of quantum mechanics. It's been tested and confirmed in numerous experiments, not with cats, but with tiny particles. And it's this principle that allows quantum computers to process vast amounts of data simultaneously, promising a revolution in computation. Quantum mechanics challenges our understanding of reality and shakes the very foundation of our logical thinking. It's a world where the conventional rules of the game do not apply. So, in the quantum world, things can exist in multiple states at once until observed. It's difficult to comprehend just how large the universe is, but let's try to put it into perspective. Imagine holding a grain of sand between your fingers. Tiny, isn't it? Now envision that this grain of sand represents our planet, Earth. If Earth were this small, the solar system would be the size of a beach ball. That's right, a beach ball. It's a pretty big leap, isn't it? But hold on, because we're just getting started. Now, let's bring in the concept of light years. A light year, as you may know, is the distance that light travels in a year, about 6 trillion miles. To put that in perspective, if we continue with our analogy, the nearest star to us, Proxima Centauri, would be over 4 light years away. That's like placing our beach ball-sized solar system in New York and the next one in Los Angeles. But the universe doesn't stop at our neighboring stars. Oh no. It extends far beyond to galaxies that are millions of light years away. The Andromeda Galaxy, our closest spiral galaxy, would be about 2.5 million light years away. In our analogy, this distance is equivalent to going from Earth to the Moon and back over 1,000 times, and we're still not done. The observable universe is estimated to be about 93 billion light years in diameter. That's billions of galaxies, each with billions of stars scattered across an almost unfathomable expanse of space. If we were to scale this to our analogy, our entire observable universe would engulf the Earth. It's mind-boggling, isn't it? The vastness of the universe is beyond anything we can truly grasp. Each star, each galaxy, each nebula is a testament to the enormity of the cosmos, a testament to the fact that we are but a tiny speck in the grand scheme of the universe. So the universe is incredibly vast, with distances so enormous they're almost beyond human comprehension. Did you know your brain is the most complex known structure in the universe? Yes, it's true. This 3-pound mass of jelly-like substance nestled within our skulls is a marvel of complexity and functionality that outshines even the most advanced supercomputers. Imagine a bustling city with millions of interconnected pathways and networks where countless tasks are being carried out simultaneously. That's your brain. It's home to approximately 100 billion neurons, each connected to up to 10,000 others, resulting in a staggering 1,000 trillion synaptic connections. And within this intricate network, electricity and chemistry combine to generate thought, emotion, and consciousness. But here's where things get really interesting. The brain, in all its complexity, is the very organ that allows us to ponder its own existence. This is the paradox of the human brain. It's a bit like a painter trying to paint a portrait of herself without a mirror. The brain is studying itself, trying to unravel its own mysteries. And speaking of mysteries, let's delve into one of the most profound: consciousness. Consciousness, the state of being aware and able to think, is the epitome of the brain's prowess. Yet, how consciousness arises from the interplay of neurons remains a tantalizing mystery. Some scientists argue that consciousness is a byproduct of complexity, while others suggest it might be a fundamental aspect of the universe, like time or space. But despite all our advancements in neuroscience, consciousness remains largely unexplained. In fact, the more we learn about the brain, the more we realize how much we don't know. It's a bit like exploring a vast, uncharted territory. With every step we take, we uncover new wonders, but also new questions. So, the brain is a fascinating and complex organ, the workings of which we are only just beginning to understand. Indeed, the brain is not just an organ, it's a universe within itself, filled with mysteries waiting to be unraveled.